Okay, everyone ready? So let's continue. Last time we already looked into 1.5. Okay, let's do some recap. What you're going to touch up on your module 5 is under our CPU. Last time I already discussed with all of you. Please remember that under CPU there will be 3 elements, which is register, control unit, and also your ALU. So you're going to go deeper. Now you're going to look into CPU first. Later on, you're going to go deeper and deeper for each elements like register, ALU, and also CU. You're going to look into deeper and deeper. So last class, we did take a look into what is the overview about the definition for fetch instruction, interpret instruction, and fetch data. There is several others like process data and write data. And we looked at this diagram, which is the correlation between ALU, register, control unit. And I inform you that with these 3 elements, similar to our bodies, we still need other things to connect our ALU, register, control unit, and others element in our computer to connect together. So we need a system bus. And a system bus also have several different type, because there will be several things when we want to connect them together for our element in our computer. So that's why you can see there is 3 things, which is control, data, and address. Whether it is line or a bus. A bus is a complete system. For the line, it's just a connection between one element to another. You also look, there is 2 principal part for CPU, which is data path and control unit. In this slide number 9, you look the differentiation or the definition between data path and also your control unit. What is their job? What is their job and what is their task? So on the data path, they are interconnected, interconnected. So it consists with ALU and storage, which is your register. 2 things. Under CPU, you have ALU, you have register, and also CU. So these 2 are under data path, which is consists ALU and a register, which is storage unit, which is interconnected, which is inter means that inside a CPU. So a connection inside by a data bus. So it is interconnected and it is connected between each other using data bus. That is also connected to the main memory. Later on, it's going to connect to the main memory. While for the CU itself, control unit, it provides signal to the data path and also memory and input-output. This is memory. You have another one, which is input and also output. This is 4 important element: memory, input, output, and processor, which is CPU. So this CU will provide a signal to your data parts. This is data parts, ALU and register, memory, input and output device, what they need to do, what to do according to instruction of the program. And you also look what is the important information about internal CPU bus. So internal CPU bus, the register are interconnected and connected to the main memory through the common data bus. So each device on the bus is identified by a unique number that is set on the control line whenever the device is required to carry out a process. So there will be two things, a separate connection that are provided between accumulator and memory buffer register, and another one is ALU accumulator and another one memory buffer register. So this permit data transfer between devices without use the main data. Here also we already discussed last time in our previous class that there are three things, and I relate that it is will be also similar with your system bus. If you have a system bus, it also will be separated into three: data bus, control bus, address bus. So similar also in your internal buses, which is your bus line. It will be divided into data line, control line, and address line. It is a set of wire that simultaneously will be convey a single bit along each other. So let's say you have a ALU and a register. So you're going to have like one line here. One line is going to go for a connection about data, communication between ALU and register. Another wire will be for control, and another wire will be address. So there will be several wires. Similar also with electrical thing. You can see there is a lot of wire, although it is just like a connection from your CPU. This is your CPU, and you have a power outlet, power wire to send to your power outlet, right? There will be like this. So you can see you need to have like plug like this. So there will be also inside this one single wire, you can see one wire, but inside this there will be several wire inside. So they have their own task or function, similar also in our bus system and also our bus line. So the component of typical bus, this also we already looked into. Three things. You can see address, data, and control bus. How it connect CPU, main memory, and another one input output device. You can see here you have three things, and you're going to connect to the wire, to the power. There will be data line, control line, and another one is your address line. So until here, last time we touched in our previous class. So today we're going to look into next subtopic, which is register organization. So still remember what is the use for register is like a temporary memory when you want to store something temporarily. So it register from the highest level of memory hierarchy. Let's say you have a hierarchy, so register will be on top of the hierarchy. Small set of high-speed storage because it is a highest level, so it is near to CPU. It's near to CPU, so it's going to be high speed. Temporary storage for data and control information. So remember this, for data and control. It is not for the address. Uh, Register hold data that can be readily accessed by the CPU. They can implemented using D flip-flop. So this is called information correlation between your COA and also your digital logic subject about D flip-flop. But what type of D flip-flop that are using is 32-bit register. So under register, you're going to have two categories, which is user visibility, you can see it, and another one is control and status register. User visibility is for general purpose, may be referenced by assembly level instruction that are those visible to the user. So it is like a reference for you to use for the assembly level. So that's why you can see it as a user, as a programmer. While for the control and status register, it is for special purpose only. What is the use? You know already, control is going to be used to control the operation of the CPU. Because you know that register in the CPU, right? Inside the CPU, so it will control the operation for CPU. And mostly you're not going to see because it is not visible for a user. So let's see one by one for these two categories. Still on the theory part, you need to know the theory before you can go further. So user visibility, under this register, it will be referenced by mean that machine language that the processor execute. So under this, you need to also know you can categorize it like this. Might be, so you can categorize it to 4 things, which is the general purpose, data, address, and condition code. And remember that it is the things that you can see normally. Mostly user visibility register, you know the data, you know the address, you know the condition of the code, and what is the purpose of the register. General purpose of register, which is can be assigned to variety of function, define the operation within instruction. Example, your general purpose of register EAX, which is accumulator register. EBX, so this is a base register. ECX, this is a count register. That's why last time in our previous module 4, we have ECX for us to use the counter as a counter because it is a count register, and EDX for the data register. So under this general purpose, you know the general type of register, and it can be used for addressing function also. So you have a register. It divided into user visibility and another one like control, and here you can divide it into general and then data register, What else? Address, and lastly, the condition of code. Later, you're going to look into deeper for the control and status register. So you can draw your own diagram so you know what inside the register. Okay, you just know last time about register. Okay, EAX, EBX is a register. But now you can see where it belong. So you can draw your own diagram to see what the inside deeper and deeper. So the data register hold data and cannot be used in calculation, in the calculation of operand address. Example is your accumulator. It cannot use for a calculation operand address. Address register, the purpose of address register function is to hold address information. So what is the example? It is for address register, segment pointer, stack pointer, and index register. So last time you have things that you're going to put into your stack, and you have a pointer. So it is the use for the address register. And lastly, the condition code or a flag. This one you can see at the output. When you play around with your Visual Studio, when you have the output dump register, you can see your EAX, EBX value, and at the end of the output also you can see like SF, ZF, so all the flag. So let's take a look. You can try to look back all the flag. You have several common flag. Later on you're going to learn it, okay, but this one is just example. What is the function? It is a bit set by the processor hardware as result of the operation. So there will be a several meaning. Sum flag is for what? Zero flag is for what? Overflow is for what? You're going to have only like 0, like ZF, or might be as a 1. So there will be a meaning for each of the flag. Can be accessed by a program but not changed directly. Example of this, and bit value of use as a basics of condition jump instruction. So here you can see your general register. This one, and the general register you have several. Last also you have like EH, EL for the register. Accumulator, base, count, data. So this one you can see also you have a pointer index. There will be several pointer and also index. Stack pointer, ESP, is a stack pointer. EB, base pointer. SI, source index. DI is destination index. So all of that have their own function. Another one, you have a segment. Segment is a code, data, stack, and extract. And lastly, program status, which is flag and instruction pointer. No need for you to draw for each diagram here, but you're going to need to understand and remember all the register. What is the meaning by the short form of the register and their function? So you can see here one by one, what is the function for EAX? it is automatically used by MUL and DIV instruction. So now you know, okay, last time you just apply it, but now you know in deep that this is the function for EAX. Purposely, the EAX automatically used by MUL and DIV instruction. Second, you have ECX, which is automatically used by processor as a loop counter. So remember last time in module 4, when you play around with loop, there is a things when you have this ECX 5, let's say, then you are having a looping. It's going to be a decrease until you have a 0. Avoid use for generic calculation. This one already informed previously in the definitions. So stack pointer, base pointer, source index, destination index, please don't use it as a generic calculation. So address register should be wide enough to hold the longest address. It depends on your program. So that's why I always remind you, okay, look at the size, whether you are using a byte, a word, what else, D words, and etc. So you need to have enough size also to hold whatever data that you are want to achieve. So data register should be also enough to hold most data type. You have address, you have data type. Will not want to use a 64-bit register if majority of your data is only 16 and 32-bit, because the rest you have just empty slot and you did not use also. So you can pick the correct size to be used. So related to the width of the memory data bus also. So there is a solution for you. Concatenate register together to store longer format. You're going to use dx equal to ax. Later on, you're going to see what is the meaning by dx equal to ax. Okay, let's say here you can see example. Assume the following dumb register. Update the, okay, this is your normal output last time when you are playing around with your Visual Studio. You have MULAX. So how you going to update the, going to have multiply your AX. So where is your AX? Of course, it's going to be here. But you can see you have, depend on the size also. So when you have AX, let's say in the AX value is 0400H. This is initial value inside your AX register. When you execute this MULAX, means that you're going to multiply it. And it will be AX multiplied with AX equal to this value. You're going to multiply 2 times. So you're going to get 100000 hexadecimal. This is the value. And let's see here, you're going to see that you have the value of your AX. This is your AX, and it will be also having a value of the X here in front. So you have the size. After you multiply, you can see when you multiply, the AX register only have this size. So you only have this size. But when you multiply both, you get this long answer. Long, okay? But you only cover until here for AX. Unless you have EAX. Then you can have the whole size. But for AX, you only get until here. So what happened to the others? So it will be for your DX. It will be updated here and your AX only get 0, 0, 0. So this is the solution if you have like too long in the answer or the data that you're going to store in your register, but it is not enough size. When you are not having enough size, you're going to use this dx ax, which is the size. When you are playing around with ax, let's say, so you're going to have this value, the rest you're going to put into your dx. So maybe you can also try to run this in your Visual Studio. Can you get the similar answer to store in your dx? So play around also, not just using 0400 hexadecimal. You can try another value, and is this one will be stored in your dx or not? And the exact size you can also save at the ax. And you have also another one which is under the ivbx. So you're going to divide the bx, and you have the initial value just now. Okay, this one is continuous. So this is the ax, and you're going to divide it with the bx, which is 0, 0 to 0 hexadecimal. So initially, you have this value. Initial, you have this value, and our initial value of EAX and EDX is here, which is continuous from this example, only it's updated the BX value. And what you need to do, you're going to divide this value, which is continue. Just now we have this on top of our command of our program. So here is the next code. You're going to divide it and you will get the 8000. So your size you already divide, you're going to have the size enough for ax. The size is enough for ax. So you're going to update the value in the ax, and the rest will be updated to the dx. So this is the concept, just for you to have a solution if sometime you already overflow, the size is not enough, so you're going to use the solution. It will be inform you that you need to use that solution or not. In the question, it will be not like too general like this. You're going to be specific inform what you need to do, what is the initial value, and normally it's going to be full, like several program will be putting inside, not just a single line like this. Okay, we continue with another one. Just now we look into the our register for visible user visible register. And now we have another one, which is control and status register, but you cannot see it. Normally it's not visible for you. So let's see what we have in our control and status register. There are various of processor register that are employed to your control to control the operation of the processor. Okay, you can see also most of these on the most machines are not visible. Just now also we know, okay, it is not visible to the user. Some of them may be visible to machine instruction, execute in control or operating system mode. So different machine will have different register organization, and it's going to also use different terminology. We have 4 essential register for instruction execution. First, we have program counter, which is PC. Last time we did take a look also with our program counter at the end of our module 4. We play around with the program counter. We have also instruction register IR, memory address register MER, and memory buffer register MBR. So later on in our next slide, you're going to apply only the short form. So please make sure you know what is the short form for BC, IR, MER, and MBR. Memory address register, memory buffer register. So what is the function for all these register? Last time you did not see as a user, because user normally can see the code like EAX, EBX, the normal register for your use. But basically inside, when you are having a code, last time please remember that you're going to have also a program counter. So you're going to count the value of your counter. So what is the function? The address of the instruction will be fetched. Instruction register, the function is the address instruction most recent fetch. For the memory address register, the address of location in memory. And lastly, memory buffer register MBR, a word of data to be written to memory, or the words most recently read. So all this table to spot a question, I already informed you. It is important when you have a table, you need to remember all the meaning and functions. Like this, let's say you have the definition, you need to remember. If you have a function also for each table, normally we just swap. We give this correct, and this two is wrong. So we just change the place. So you need to pick which one is the correct function for all the register. So you need to carefully remember all the things. The 4 register that mentioned just now are used for movement of data between processor and a memory. Not all processors have internal register designed as MAR. So you can see just now I mentioned to you, but after this we will use the short form. So please make sure you know already. This is for memory address register and MBR, memory buffer register. It needs some equivalent buffer mechanism to store the bit transfer, read bit to and from the data bus. So there will be important things that you need to remember, that ALU have direct access to MBR and user visible register. So it have a power sometimes to have a direct to your memory buffer register. There may be also additional buffering register instead of MBR at the boundary of ALU serve as input and output register for ALU and exchange data with the MBR and user visible register. Okay, here you can see the picture for your computer, of course, because we are playing around with a computer and organization architecture. The CPU exchange data with memory. So you have a CPU here and you have a memory and also CPU. So how they are changing the data between themselves using a system bus. So in a memory, you have like instruction, you have a data. This one is a total number of the memory, how many you have in the size. In your CPU, you have a register. Now you can see you have the PC, IR, MAR, MBR. You have also another register as mentioned under MBR. Just now it's mentioned. Okay, you can have additional buffering register. So all of this under CPU, remember you have register. So this is all under register. And then you have another one, CU. You have another one which is ALU. So there will be many. Last time you just see only 3 things under CPU. ALU, register, and CU. But inside here, when you go deeper and deeper, you can see inside here, oh, actually it's a lot. This one is just one thing. But for user visibility, there is another, like EAX, EBX. So a lot of under only one, which is register. Okay, this one is connection for the input, output, your input device, keyboard, your output, your display. So it is a connection to each other. So this is the just now you already look into these 4 things, but you have also additional, which is input output address register, IOAR, input output BR, input output buffer register. Is it okay? So no need for you to remember to draw. There is nothing just to draw, but might be you need to know inside of this what is available. Go deeper and deeper. You can draw your own picture, which is last time in our previous module you have only 3, but after that, let's say this is R, then you can draw it like this. Okay, inside here you have what? Okay, you have a user visibility and control. And after that, for user visibility, what type of register that you can have? EAX, EBS, ESI, etc. So in here also, what will be available for control? So you have a PC, you have MAR, you have IR, so you can see the coloration. Or maybe you can try to draw a bigger CPU picture, so you can put all the things. Then you can see, oh, actually in CPU there is a lot of things. It is just one thing now. You just look into the register. After this, you're going to look into the control unit and etc. So let's see here. After this, you're going to go deeper and deeper. So there is a lot of function and also things inside of the register that you need to know. I guess we stop 5-minute breaks. After this, we continue with our next slide, which is instruction pointer and the rest. So again, you're going to see there is a lot of theory things before you can play around with the coding, with the calculation. So before that, you need to memorize and understand for each function. Okay, so let's stop 5-minute breaks, and after this we're going to continue. Okay, class, let's continue with our next slide. Everyone here? Share the QR code. Okay. Okay, this is the QR code. Okay, let's continue. Please enable your webcam. We will continue with our next slide. Okay, let's continue with instruction pointer. So for instruction pointer, the extended instruction pointer EIP register hold the address of the next instruction to be executed. So the EIP, or the short form for extension instruction pointer, is corresponding to your program counter just now, which is PC. In other architecture, so they're having a correlation between each other. EIP, or extended instruction pointer, can be manipulated for certain instruction, like you're going to use this for a jump, a call, return to a branch to a new location. So that is the use of your pointer. So you have several instruction pointer, which is EIP, that you need to know, extended instruction pointer, and it is also having a correlation between your program counter. Program counter are using, where is it? Program counter are using also when you are play around with the jump statement. Where is just now the slide? Forgot already. It's okay. After that, you also need to know on a program status. After this, you know that there will be a meaning for each flag that occur in your output. So a program status, many processor design include your register or a set of your register, which is often known as a program status word, or PSW, that contain your status information. Maybe your program error, maybe your program have warning, or maybe you have the outputs that's overflow. Maybe your program have any other information, and also about condition of your code for your program. So it is under your program status word. The ALU has number of status flag that reflect the outcome of the arithmetic and bitwise operations. So how you can see your status of your program? So one of that is under your ALU, which is your flag status. So let's see what flag and common or general flags that we always use. So we have several flags, which is ZF, zero flag, SF, which for sign flag, PF, parity flag, CF, carry flag, and lastly overflow flag. So whenever you have the output, you have the set of register EAX, EBX, ECX, ESI, blah 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 blah, and you can see that you have like ZF, SF. So it's depend on the functions of program that you are written. And you're going to see, still remember what is the meaning by set in the geontology subject? So it's going to be 1 when destination result equal to 0. So you're going to have 1. Or otherwise, you're going to have 0. Okay, so for 0 flag, it is for you to check the destination, whether the destination is equal to 0, which is the result equal to 0 or not. So if it is 0, then you're going to have the value of your ZF equal to 1 or set. While for your sun flag, if your result is negative at your destination, of course, if it is negative, you're going to have SF equal to 1, which is set. If you get SF is 0, then you have a positive. While you have another one, is parity flag. You're going to have PF equal to 1 when your result has a even numbers of 1. So you need to calculate. You need to calculate if let's say you have 101110. Let's say this is your answer. So you're going to calculate how many bit 1 has even number of bit 1. So if it is even, then you're going to have PF equal to 1. You have 0, then it is odd. For carry flag, we're going to have equal to 1 when unsigned value is out of range. And lastly, overflow. This is a general flag that available. For the overflow, we're going to have equal to 1 when signed value is out of the range. So it's quite similar, only the difference between unsigned and signed number. So please make sure you remember now, okay? Then you can refer back at your output. Okay, what is all the function? You can see 0101 at your flag. So now you understand how to check the flag. And lastly, you can see you have the auxiliary flag, AF. When there is carry from lower nibble to higher nibble in lower byte. So you're going to have equal to 1. So your status flag will reflect the output, will be depend on the output. So it will show whatever output, then it's going to see in your flag of the arithmetic, which is content of destination operand. So we have example here. Assume that you are using add bit system. You're going to add these two numbers. So when you add these two numbers, what happens? So you're going to store this into your destination operand. So it will affect your flag. So now you can see here operation result. So this is the result. It is not 0. That's why you're going to see so ZF equal to 0. If you have the 0, then you're going to have 1. So please make sure you remember back whether your result is 0 or not. If it is 0, then it will be 1. If not, you're going to have 0 for ZF. And you can see, calculate the value of 1. It is for what? It is for parity flag. You need to calculate whether it is even or odd. How many digit 1 that available? So you have number for digit 1 is equal to 4. So it is even. That's why your parity flag will be equal to set or a 1. So about a sign, you can see sign number, it is positive number, so it will be 0. It will be set as 1 if it is a negative. So you can try to look into the rest. This one, this one. So this is just now we look into. So next, we have also here another example. So you're going to use similar add bit, and now you have like overflow. Here I can see. So how many digit numbers you can depend on the parity flags. So whenever you have here you have odd. Just now you have even. Okay, so this one is I think wrong. So you need to have even for 1. If it odd, it's going to be 0. So please correct your answer or your slide if you get a PF here as a 1. Because our odd number is 1. And then, our odd number supposedly will be 0. So there is a carry. You can see here a carry from your lower bit. This one is lower bit and this one is higher bit. So nibble. See nibble, how about nibble? To the higher nibble, so it's going to be set if you have this condition. So you have this carry, that's why you have AF equal to 1. There is a carry out. So just now I mentioned, right? There is a carry, so it will be a carry also. Set as 1. So you can see also what you need to update. Assume the system use the word of size for assume the size use double size for this question. So you can try to do it, and this is the solution. And what is it? Sorry. Okay, so you can see about whether at the lower bit to a higher bit, is it have a carry or not? So similar also for nibble by nibble. You can see whether they are having a carry or not. And inside here, is there any carry or not? About the sign, of course you're going to have it's 0 because it is not a 0 for the result. The total number here, how many digit 1? So all of this you can try by yourself also. It is not too hard because it's already give you the instruction carefully in the slide 34 here. So there is several example. Solution A, solution B also for another example. So it is word size word. You know how much word size, and another one is double word. So if double word, what is the difference? Similar question, only the size is different. So can you get a similar flag with the double word? So you're going to get a different. Try to do it and to test whether you're going to get a similar or not. So here is word size. Or here is mentioned already. Word size. Here is double word size. So you see whether you get similar answer or not. So this is the only thing that affect, and also the red color. Depend on the size, right? Okay, you have also several other example. Now under example 4, you have 3C hexadecimal minus 28 28 hexadecimal. So you need to use your parity, your even parity for this question. So you're going to have even parity, going to use the complements. Why? Because you have the minus here. You're going to change this to be addition. Remember, if you try to change, it's going to be 3C hexadecimal plus minus 28 hexadecimal. This minus you're going to change to be a second complement. So it is a method to use the even parity. If you still remember last time in your previous I guess you learned also in digital logic subject in earliest our module, and you change this to second complement. I hope you know already how to get 28 hexadecimal. You change to be negative number using a second complement. It just changes to be a second complement, and this is the result. So you're going to get 10010100. So using this answer, you need to update your flag about the ZF, SF, CF. So all of this we already discussed. What is the function and how you're going to get the value. And what else? Okay, next you have another example B. So example B also you can see you have you need to change this to be a second complement. For second complement, then you just add. So you need to update your flag. So please try to do also in terms of coding. You write your own coding. Like maybe you have move EAX, the direct value. You just use direct value, simple. 3C hexadecimal. You already move to here, and then you just do like multiply, and not multiply, subtract. Or maybe you just using it number. So you subtract EX with the value of negative 28 hexadecimal. So you try to look your answer, and you will get to see what is your output in terms of the sign. So try to do it. And there is several other exercise you can try also using your Visual Studio and compare with your manual answer. You try to solve it manually using two's complement and also using the Visual Studio, whether you get a similar status flag or not. So you're going to have design issues of your control and status register organization. You have several issues. All our system is not perfect normally. We're going to have several issues. One of the issues is under our operating system support. Another one is on the allocation of control information between register and memory. So first one, operating system support. Certain type of control informations are of specific utility to the system, to the operating system. The register organization need to some extent to be tailored to a particular operating system. And for second, uh, the allocation of control information between register and memory. The designer must decide how much control information should be in the register and how much in memory. And another one, the usual trade-off of cost versus speed arise. So this is the issues that normally or general you can find. So you finish already on the register organization. Now let's take a look into instruction cycles. So you're going to see the background first on the overview, and then you're going to go directly to the indirect cycle information, and last on the data flow. The process require you a single instruction, and every single instruction we call instruction cycle. So there will be a several stages, three altogether in our instruction cycle. First is fetch cycle. Second is execute cycle, and third is interrupt cycle. For fetch cycle, fetch instruction, so that will be the tasks or the functions of fetch cycle. It's also used for decode, and another one, fetch operand if it is indirect for the instruction given. Second one, execute cycle, which is perform the operations and also store result if also it's required. And lastly, interrupt cycle, which is recognize pending interrupt. So here is the example flow on your instruction cycle when you have interrupt. So when you have interrupt, this is how it's look like. So you're going to try to do one by one, execute your following program. So let's say you try to point at line number 5. So you're going to fetch or try to solve the one single instruction. So it is under this circle. So first of all, you're going to fetch the instruction, which is try to fetch the instruction, next instruction. And you try to execute this instruction. So maybe you can see you're going to have interrupt enable, of course. Then you're going to check whether you have interrupt or not. Might be you can try directly get the output. But if your interrupt is enabled, you're going to check first whether you have interrupt or not. So this is the interrupt cycle. You're going to go back if there is a interrupt after you check. So you also can disable the interrupt. You can also disable there is a disable interrupt. It's depend, but you need to check a condition whether you have an interrupt or not. And this is a fetch cycle. This is the execute cycle, and lastly interrupt cycle. Program executes halts only if the machine is turned off, some sort of unrecovery error occur, and another one a program instruction that calls the computer is encountered. So there will be a 3 executions if you have the interrupt and goes to the host. Well, when you have the uh, indirect cycle, what is the cycle look like? So you're going to see the indirect addressing, which is you're going to have another instruction stages, because you need to fetch the data indirect, right? If direct, you can see direct address, you get the value. But now indirect, you need to check the value for the address and you go to the inside of the stack. So it is indirect. So when it's indirect, you need to have another stages because you need to check inside. The main line of activity consists of alternative instruction fetch, instruction execute. So just now you can see you have fetch, execute, interrupt. Fetch, execute, interrupt. So this is a direct cycle. For indirect, you have another one, which is indirect. So following execution and interrupt may be processed before the next instruction fetch. For just now, you have fetch and then you have execute cycle, you have interrupt cycle. But for indirect cycle, you can go to the execute or direct to interrupt and go to back in for the cycle instruction. But when you have interrupt, you can go to the indirect, you can go to execute, back to fetch. Or might be you directly go to the interrupt and for the fetch. So you have another one more stage to add on. So you have also another way to view the process, which is shown in this, which is more correctly nature of instruction cycle. So this is the instruction cycle state diagram. No need for you to remember all detail. I don't think that we're going to put like A, B, because there are too many things that you need to remember. So let's say we have the instruction fetch, instruction address calculation you were given. Then you're going to have instruction fetch. You're going to go to the instruction operating decoding. Try to find out what is the operand address calculation. You're going to have, if needed, you're going to go to the indirect direction, which is you go back to the operand fetch and go to the operand addressing. So you can see also there will be a data operand calculation. Maybe you can try to look into one by one for this cycle, but no need for you to remember all the element inside. You need to just to understand the general overview, quite similar, but the things that important is the general overview, instruction cycle with interrupt, and the general for the indirect cycle. So after you understand these two, then you can easily understand what will happen. So start in the instruction fetch. You go for the instruction operation decoding. You're going to find out the operand address and operand fetch. Continue with the data operation. You proceed with the address calculation. If your instruction mentions about the address, might be you +1, +2, so you try to calculate it. And actually, you're going to also have the storage for the answer. And when you have fetch, you execute, you're going to check your interrupt. So whether you have the interrupt or not. So you have interrupt, you go back. If there is no interrupt, you're going to go also back to whether you are going to the fetch or you try to execute again. So you have two things. So that is under your cycle for the fetch cycle, execute and interrupt. You only have these three stages. When you have indirect, you have another one stages. That is only different for the general instruction cycle. Now, let's see on the data flow. How the data flow will be deal with our cycle just now. The exact sequence of event during instruction cycle depend on the design of your processor. So under our processor, we have a lot of register. If you still remember, so this is the things that our processor employ. We have MAR, MBR, PCIR. So each this smaller cycle consists of series of steps that involve the processor register. Here is the processor register, or we can call it as a micro operation. So just now you know the general cycle. You know a general cycle only for the instruction cycle. But actually, when you are playing around with the data, you can also divide it into several, depend on your processor. So here, conventional format is using register transfer language, RTL. So you can see you have the IP IP+1. This is example that you are using the register transfer language, or might be you are using a program counter. You're going to have adding for the program counter value. So if you have a point at the register address of 500, so when you point to next, you're going to have +1. So we're going to go deeper for our micro operation later on in our subtopic 5.5 and 5.6. Okay, under our fetch cycle, we're going to go deeper. Just now is our general part. On our data flow, later we're going to discuss in deep at 5.5 and 5.6. And here is the general flow for indirect cycle and for a instruction cycle for the interrupt. Later on, we're going to go deeper at fetch cycle, execute cycle, interrupt cycle. Just now, you know, there is 3 stages for cycle. Cycle, you have fetch cycle, execute cycle, and interrupt. If you have interrupt, then you can go back. Or might be if you don't have interrupt, you can go back also. But when you have indirect, you might also have the indirect. So you can go here, or the indirect might be this having an interrupt, might be also is going to go back. So there will be a general things that you understand. Now we go deeper for each flow. fetch cycle. After this, we're going to look into the second one, execute cycle, and then interrupt cycle. So let's see under our fetch cycle. You already know the function. So you already know the function. What fetch cycle will do? So it's going to fetch the instruction. It's going to decode the instruction. If needed for the indirect, it's going to also fetch the operand. So this is the function. So let's see what and how it's going to do under our fetch cycle. So an instruction is read from your memory. So just now you remember fetch cycle going to fetch the instruction. Fetch the instruction. So where you're going to fetch the instruction, you're going to read it from a memory. So this picture are showing the data flow when you are doing the fetch cycle. So let's say here, first of all, you can see you're going to have you have MBR here, you have PC here. So PC will try to get the instruction from your memory. So this is memory. So it will be sent to your CPU. After this flow going to find and fetch the control unit will inform PC to get from your memory. Memory will return back and it will be also dealing and go for the MBR and lastly for IR. So first of all, what you need to know is it will fetch the instruction from your memory. For your memory. The fetch cycle can be written also in symbolic using RTL. What is RTL? Again, it is register transfer language. And there is two examples given here. So you can be also written symbolic using RTL. So let's say you have MAR. So you have MAR here. You going to get the informations of IP or PC, which is pointer, to go to the MR. So the value of pointer. What is pointer? A program counter. When you have a program counter, you're going to check and it's going to be under our MAR now. MAR will equivalent to pointer. Next, you're going to have, okay, you're going to see first one by one for T1. So this PC or program counter contain the address. Of course, this address is content of your is going to be content of IP and PC, and it's going to be loaded to the MAR. So similar also is like MAR equal to PC. Similar. Okay. Using the RTL here. What else you have? Next, you have under T1 here. Still you try to fetch data from instruction. Then you're going to transfer to your memory on the address bus. So here, PC is equivalent to MAR. So it's going to go to the address bus next to go to the memory. So this is the first one. It will be transferred to memory using your address bus. After that, your CU will active the read signal of memory. So CU will instruct an active signal for read signal of the memory. So you finish one single line. So this one, we try to go to the memory and control unit will send to your memory to activate it. After that, for T2 here, it's going to be instruction is accessed from the memory and transferred to CPU on the data bus. So instruction will be fetched back to the memory, and memory will be using a data bus. Go back to the CPU. Go to the CPU first, okay? So this is a CPU. After your CPU, okay, here. After that, this instruction address will be loaded into your MBR. So you send to the CPU using data bus, it's going to be loaded to your into your MBR. Done this one, and lastly, you're going to do MBR equivalent to IR, IR equivalent to MBR. At the same time, your PC or IP will be incremented point to the next instruction. So you know when you have a program, step over, after you finish one instruction, you're going to be increased to point to next. But here now you can see you already finished the flow just now. So when you pass back using data bus to your CPU, MBR will be taking place. After that, you have the last one, which is instruction MBR is loaded into your IR, which is instruction register. The opcode of instruction will be decoded and translated so that determine the micro operation for particular instruction. For a single instruction, so you try to determine it. So that will be a flow. For the fetch cycle, normal fetch cycle without the indirect cycle. Okay, without the indirect cycle. So this is the neural flow that you need to remember. Now let's see our fetch cycle, still similar, but now we have indirect cycle. You did not have the only difference, you did not have IR and also the PC. Once the fetch cycle is over, the control unit eliminate the context of IR just now, right? After you have the IR, then you're going to see to determine the context or operand specifier using your indirect address. So you will have the value for indirect cycle on the IR. Then you're going to go directly to the flow, exactly quite similar to the previous one. So this is the data flow for indirect cycle. Let's take a look. It will be having a similar process, one by one, T1, T2, T3. It's going to be sequential. So for fetch cycle for indirect address, can be also use RTL, similar also like a previous one. In this one, you did not have program counter, you did not have IR. First of all, you're going to have, when you have direct, so the IR actually already contain with the indirect address. When you have indirect cycle, you already have the content of IR. That's why you did not have IR. To be loaded to your MAR. Just now, MAR is equivalent to PC or IP, isn't it? But now you're going to have indirect. So that's why you are using the IR. Then it will be transferred to your memory. Similar step. You can see using the address bus. Similar also. So next also it is also similar step. So the only difference for step T1 is this. Second one, still similar, which is you're going to go to the CPU and it will be loaded to MAR. Similar thing. There is no difference. Then at the T3, it will be the data MBR is loaded to IR. So you're going to store, which is also similar. Then this one also similar. So here at the beginning, you can just use the IR instead of IP and also the PC. The rest is similar flow. So let's see the example of indirect cycle. Example 5 for indirect cycle. Involved with fetching data from memory before initiating the execution cycle. So you have the add AX, you have the indirect cycle here. Indirect cycle, yes. Indirect instruction. Of course, you need to have indirect cycle. So how are you going to do? This one is totally similar with our previous general flow for indirect cycle. So first, you have the control unit request the memory read. You have the information from your IR. So here, second, and the result is placed on the data bus. This one is actually already done with the step number 1. So here you have from the memory, it will mention, okay, this is the A at AX2400. So this one, it will be copied to the MBR for the instruction because you try to fetch the instruction. Then you're going to use this address to the MAR. Move to MAR. Actually, this one is the first thing. Before this, you have the O value. After that, you will continue similar things. Then you will place the address to your MAR. You will continue using your address bus to request to the memory. And control unit will instruct the request memory read. It will continue the flow. Okay, so it will be continuous. So that is on the indirect cycle. So actually you can direct start with this number 4 if you have the IR value like this. If the IR content with the indirect address, you load first to MAR. But this one, actually you try to start first. So that's why you need to have the control unit will activate the read signal for the memory. Okay, so you start here at this example number 5. You start at this section. Okay, you start here and memory will reply using data bus. Actually, it's similar. It will go to the CPU, and then it will store to the MBR, and then back to your MAR. it will continue to the next pointer. Okay, next we continue with execute cycle. Just now we just tried to fetch. We tried to fetch the instruction. We did not do anything more than that. We just want to fetch the instruction. After we done, we will continue to execute. Whether the instruction just now instruction is 8AX2400. So we want to fetch only the instruction. But we did not execute like add AX using the information. We did not execute. So now the execution will be continuous at the next step. So execution cycle. The opcode of instruction of IR will be decoded from previous fetch instruction cycle, and relay control signal will be generated. So this is what will be happen. You're going to have several opcode, which is processor memory, processor input output, data processing, and control. Again, for the table, you need to memorize all what is the operation, all the definitions or sentences you need to memorize, because we just play around with the sentences and we change the place. And normally it will be asked in your multiple choice question, MCQ part A. So let's see the example 6 here, example of program execution, which is content of memory and register in hexadecimal. So you will given with the program execution, you already fetch, okay, you done with the fetch cycle. Now you want to execute cycle. So here you have the value of 940 for the address. You need to add the value in the 941, and you're going to store the value in your 941 as the answer. So this is the fetch instruction that given. So first of all, step number 1, you check the program counter first. Okay, actually in the question supposedly it will mention where it's going to start, initial address, initial your pointer. So at the question it's not clear where it's going to start, but now we have the clue because it's already mentions we're going to start at 300, address of the first instruction. So you go the value of 1940 in the hexadecimal is loaded into IR. So you need to play around with the size. Okay, you need to know the size. So this inside the memory, which is we start at 300. Our offset start at 300. You look into the value. You're going to take this and put it into your IR. The same value here. And your PC later on will be increased from 300 and then go increase to 301, 302, and etc. So that is the first step. For second step, the first 4 bit, which is, you can see it is 1. in the IR. If it is 1, it's going to indicate that you're going to load the AC with the fetch data. So where you going to take it? You're going to take after this. Okay, that's why you have the value of this addition. Okay, now first of all you have the address start, and you look into the memory data inside. For this, you're going to copy the value and put into your IR. Put into your IR, and this first 4 bit will be indicate whether it is going to load or not load to your AC. If it's 1 here, it's going to be load to your AC. But where you're going to load? So you will look into another 3 bits. The remainder 12 bits specific the address. So after that, you're going to see you have 940 from the data to be loaded. So that's why after that you go to these addresses. So you're going to take this, and where you're going to load? You're going to load it to your AC. So you go to this address and load the data, put it into your AC. After done that load to your AC, what you're going to do is the next instruction for your IR here is fetch from location 301, because just now your pointer already increased. Just now you finish already to load to your SC. It will continue cycle doing similar thing. You check here, you check the answer, you load to IR. And you're going to see that this value is not 1, and it's going to check the value of these addresses 941. You can see this 941 is 0002. So 5, the old content is 0003, and the content of location just now the new one is 002 are added to your AC, and you're going to store back to AC. Unless this one is 0, you're not going to update or load to the AC. But you have 1, 2, 3, 4, 5, which is integer number more than 0. You need to take this value and go to the exact address. You have this value. Supposedly you're going to load to SC, but inside SC they already have their own value. What you need to do, you're going to add them and store back to your SC. So here, let's say you want to continue again. So our pointer now already increased. After increase, what will happen? When we increase, we have the value of this. We copy and put the IR, which is similar thing. And from here, we have the similar address. So from here, we go into the content of SC will be stored in the location of 941. So here is the step by step. So the last one, you can see you tag this, you tag from here, you adding it together, and it asks you to store final value to 941. So you will be increased. This one will be taken. So you can see it will be 241. So you will tag the value here. You can see it is 0002. But for this value, you're going to, later on, you're going to replace it. It mentioned as a replace to the 941. So the value where you're going to tag it, you're going to tag from the AC. So it is depend on the instruction. So in this question, it's not clear instruction. It's just give you the simple code here. But you can see it's only additions, and after additions, you're going to stop and store the 940 into the 940. So this is the summarize, which is step by step what you're going to do. And let's see the summarization. You start at PC 300. Supposedly in question it will mention where is or what is the value of PC. So for the first instruction, supposedly instruction also will be clear in a question. So final exam or test 2 will be clear instruction. The instruction will be consist of the value. You can see at the 300 just now, we have this value. And it's going to be load to your register and your PC will increase. So where you're going to put, you're going to put to your IR. So first 4 bit in IR indicate that AC is to be loaded. The remainder 12 bit, you're going to find into the addresses. The next instruction will be because your PC will be increased. So it will be 301, and you look into the data, you're going to have this value. And again, your PC will increase. The all content of AC contact with the 941, just now the value, and you're going to add and store it back. The next instruction, it will be 294 at 302. It will be increased again, and you're going to fetch this data 941. So actually it will be mentioned, okay, this one after you fetch these two, it will be stopped and stored back to the specific address that given at the last. So SC will be stored at 941. So supposedly in the equation, it will be informed the fully instruction. But here is just give you the very simple one, but you need to know how to follow the step by step. And the value inside also will be different. So let's see on the first cycle, and also the correlation when you have indirect cycle. Directly go to your education cycle. So later on in your test 2, I don't know whether it will be having the table, or you can just need to scroll. There is a like point drop down or etc. to you to pick up the value, but you need to also be familiar with this kind of table. How we're going to cover, I have, okay, might be I'm going to give you example of this example in a next video, because it is very important also to you to remember and to understand how you're going to relate and put all the value. Just begin mentions and give with the table. Okay, so I will add another video to your YouTube and that's specific for the example, because we need to continue our module 5 with another subtopic and try to finish as soon as possible for our module 5, because I think it will be also important for your test too. Okay, so I guess we already achieve 10 a.m. Yeah, so we're going to stop our class.